This conference will now be recorded.
Hello everyone. We'll start with uses of alkene, and with this alkene part will be complete, and after that we'll start alkynes, that is having hydrocarbon having CC triple bond. And there we will start with structure of alkyne, that is structure of triple bond, then isomerism, nomenclature, and after that there will be preparation of alkynes. So uses of alkynes. Here the first point is mentioned that lower members of the family are used as fuels and illuminates. So for the lower member, if we consider combustion, so in combustion reaction there is a generation of energy because they are exothermic reactions, so they can be used as fuels, and light is also generated, so that is the reason they can be used as illuminates. Then if we talk about ethene, which is the first member of alkene, ethene or ethylene, any of these names are correct. So ethene or ethylene is employed for the preparation of ethyl alcohol. So ethene is CH2, double bond CH2, and from this we can make ethyl alcohol, that means CH3 CH2OH. So 2 carbon containing alcohol we can prepare. So ethene is the starting material for the ethyl alcohol, and also starting from this we can make the triple bond. So here one hydrogen will be less from both sides. So this is ethyl alcohol, sorry, ethylene glycol, not this one. So ethylene glycol is where 2 OH groups are added by breaking one pi. So for the formation of these two hydroxy group containing compounds, we can use ethylene as the starting material, and the other applications are artificial ripening of green fruits, then oxygen ethylene flame for cutting and welding of metals. So these are the applications of ethene. Then in general, if we talk about alkenes and substituted alkenes, they can be used as the starting material for polymerization. That means the individual molecules will be the monomer in the formation of polymers, and they can form a number of useful polymers. And some preparation, that is the preparation of polythene, which we start from CH2 double bond CH2, that is C2H4. Then starting from propene, polypropene can be produced. So these two applications we have already seen in the chemical properties section of alkenes, but there are some other polymers also, their formation is possible, PVC, Teflon, Orlon. So details of this basically that is under the chapter of polymerization, but this is important application of alkenes. Then alkenes are also the starting materials for some other important organic compounds. For example, alkyl halide. So starting from alkenes, this is the general structure of alkenes, we can prepare alkyl halide. That means we can prepare RX where we have some alkyl group and there will be halogen. Then we can make ROH, that means alcohol. Starting from this we can make aldehyde. Then starting from this we can make ketone. So different types of reactions are possible, and we have already seen some of these applications in the chemical properties section of alkenes. And also we can produce acid. Even if it is not the direct formation, suppose direct formation of RCOH, even if it is not possible, it is possible through formation of some other compounds. But ultimately we can say that these alkenes, they can be used as a starting material for the preparation of so many different types of compounds. So these two you can easily remember. In the last class we have seen that when there is addition of if we say addition of HX, so one H is added to one carbon, another X is added to another carbon, then ultimately what we get some alkyl halide, right? So that is why we can say that this can be used as a starting material. Not necessarily these R groups will be same, so I'm just putting a R prime. Don't think that from this we will get 2 molecules of RX. No, that is not the thing. So when you add HX, basically you get alkyl halide. Similarly, when we add one hydrogen atom to one CC double bonded carbon and we add one OH group, what we get? We basically get alcohol. That means R prime OH formation is possible. So these are the different uses or applications of alkenes, and alkene part of hydrocarbon chapter is complete. Next is alkynes. Now alkynes, there will be CC triple bond. In the previous one you have seen CC double bond, now it is CC triple bond. So at least one CC triple bond must be there. It may be more than one, but at least one CC triple bond must be there. Now if you compare alkynes with alkenes or alkanes, what we will see that here number of hydrogen atoms are less. So number of hydrogen atoms less in alkyne compared to alkenes and also compared to alkanes. And what is the general formula? General formula is this one, but remember in the bracket it is mentioned when there is only one CC triple bond, then only this general formula you can consider. Now remember, what about in case of alkane? In case of alkane, we have seen it is CnH2n plus 2, but now it is minus 2, and when it is alkene, it is simply CnH2n. So these are the differences. Now here you can call it as if it is 4 hydrogen difference or 2 degree of unsaturation. Now 4 hydrogen difference means if you simply compare with alkane, look at this. Suppose you have this alkane, this one. What is this alkane? This is basically CH3, CH2, CH3. So in this CH3, CH2, CH3, obviously this is alkane, but if you count the carbon, it will be C3, then H2n plus 2, that means 3 into 2, 6 plus 2, it will be 8. And it is actually 8 hydrogen. So C3H8, and it is H2n plus 2. Okay, so this is saturated. But when you are removing total 4 hydrogen, then only you are getting CC triple bond. So here in the left hand side you can see this is propyne, 3 carbon, 1 CC triple bond. So in this case, now the general formula it will be, it is C3 and H2n minus 2. That means 3 into 2 is 6 and 6 minus 2 is 4. So C3H4, which is matching with Cn H2n minus 2. So if you compare these two general formula, basically total 4 hydrogen atoms difference. Just compare left hand side and right hand side. So this is called 2 degrees of unsaturation compared to alkane. But if you simply compare with alkene, where already one unsaturation is present, then the difference is only for 2 hydrogen. And then you can call it as 1 degree of unsaturation. But in this case, it is, if you compare with alkane, it is 4 hydrogen difference or 2 degrees of unsaturation. Now we have some examples, and also see here the YNE part is red mark, because only in this part, if you simply consider the nomenclature, that is for 2 carbon, the corresponding alkane is CH3CH3, or you can also write it as C2H6. So in this case, what we call it? We call it ethane. That means ETH, this part is common, but now it is, instead of ETH, this part is common, but instead of writing YNE, we write ANE. So ANE, you have to end with this YNE term because it is having CC triple bond. Then when it is total 4 carbon, the name is butane, C4H6. Then it is 2 carbon, and then the next example we have total 6 carbon, and it is called hexane. Also you can say the position, that is hexane, the triple bond position can be, it is in the middle part. So it is 1, 2, 3. 3 hexane it is actual name if we consider. But these are the different examples of alkynes. When it is di-substituted alkyne, that means just check whether both sides of CC triple bond you have alkyl group present or not. If it is present, that means it is di-substituted, because only mono-substitution is possible. Carbon having valency total 4, and out of these 4, 3 is already fulfilled with in the triple bond formation. Only 1 valence is left, so that is why it is mono-substitution both sides. So it is called internal alkyl, or you can say non-terminal, because it is in the middle part. Both sides you have alkyl group. You do not have any H. When it is mono-substituted, that means only one side you have R group, another side we have H. Now this is mono-substitution because we just have one R group, and the unsubstituted one will be simply ethyne. That is the first member of alkyne. So this one and this one, where at least one C triple bond CH, this fragment is present, then you can call it terminal alkyne. And the important difference between terminal and internal alkyne is that this hydrogen is acidic in nature. Now why it is acidic, details of this we will discuss later. And because of this particular character, that is because of the acidic nature of this terminal hydrogen, which is present only in terminal alkynes, there is separate unique chemical properties we can observe for alkynes, which you will not get for alkene or alkane. It is only for alkyne, because when this H is removed and there is negative charge over carbon, that carbon ion is very, very stable because of high percentage of S character. But that we will discuss separately. Right now, just remember, whenever you will have mono-substituted alkyne, that is at least one hydrogen will be attached to CC triple bonded carbon, then there will be some acidic nature for that particular alkyne. They can act as starting material for the synthesis of large number of organic compounds, and how they can be used as a starting material, everything you will see under the chemical properties section of alkynes, rendering their importance in organic chemistry. So this is the importance because they can be used as a starting material for different types, for preparation of different other organic compounds. Next is structure of triple bond in alkyne. Remember, in case of alkenes also we have a separate heading, that is structure of double bond. But now we will discuss structure of triple bond in alkene. Carbon-carbon triple bond in alkyne. As we know, before pi bond formation there is always sigma bond. So one sigma bond and rest of the two bonds out of three, they are actually pi bonds. Now to understand in detail, we just have to consider the hybridization. Let's have a look. Carbon, as we know, it is if you only consider the outermost shell valence shell configuration, it is 2s2 2p2, right? So it is, if it is 2s2 2p2, but in excited state what happens? The electron pair in S, that is broken, that is this will be shifted to 2p. So now you can see total 4 separate electrons, and this is the reason why it is tetravalent. What type of hybridization we will consider here? It is sp hybridization. That means 1s and 1p. Now when it is 1s and 1p, there is generation of total 2 sp and 2p orbital. They are still pure. They are not part of hybridization. They are pure p orbitals, right? Now these 2 sp, that will be used for sigma bond formation, right? And these 2p, that will be used for pi bond formation. Now if you simply consider the simplest molecule, better we start with this. So in this case, this is one sigma bond, this is another sigma bond. Just focus on any one carbon atom. This carbon is using its sp orbital for bond formation with H. Now, not necessary here you will have H, you can also have some other R group, but whatever it is, whether it is H bond or any other cis methyl bond, that is CC bond, whatever it is, carbon is using its sigma bond, right? Similarly, this is also sigma bond, whether it is H or R, whatever. I'm just writing it like this. And the second sigma bond, suppose this is carbon number 1, carbon number 2. So I'm just talking about suppose carbon number 1. So carbon 1 is using one sigma for one H or R. Another sigma it is using for sigma bond formation. Another sp is used for sigma bond formation with carbon atom, second carbon atom. And these two are pi. That is carbon is using its two pure p orbitals for bond formation, pi bond formation, and that is with the second carbon. And the same explanation is also true for the carbon number 2. So in this way you can understand the sp hybridization. Fine. Now, if that is the case, let's have a look in this orbital diagram where we have this HC triple. I'm writing in the same fashion as it is, as you can see in this orbital diagram. So carbon, suppose this is carbon number 1, this is carbon number 2. So carbon 1 is using its 1 electron for this sigma bond formation. So this is the sigma bond. Carbon is using another sp hybridized orbital for bond formation with another carbon. So this electron is coming from left hand side carbon, another electron is coming from the other carbon. Now 2 sigma bonds done. Next is, suppose if this is happening in x or y, x axis. If this is happening in x axis, then I will say that this P is basically Px. This is Py, this is Pz. Now it is not necessary that hybridization will be with Px only, it may be Y or Z also. I am just arbitrarily saying if it is in the x axis, that is a molecular axis where the HCCH, this fragment is present. If it is in x axis, then what happens? This is the, suppose, y axis, and another one will be z axis. So these two are z axis. Okay. So one pi bond will be between py of carbon number 1, py of carbon number 2. Similarly, the second pi bond, that will be between pz of carbon number 1. Suppose this is z, and pz of carbon number 2. So here the yellow orbital, that is for suppose pz, because it is in the z axis, and the blue one, that is in the y axis. So in this way 2 pi bonds will be there. Now what happens, though here you are seeing this electron cloud, these orbitals are basically electron cloud separately. You can separately see here the blue electron density, the yellow electron density, but ultimately what happens, these 2 pi bonds are mixed together in such a way, ultimately they becomes cylindrical type of shape, and that picture we will see in the next slide. So I hope right up to, until now this picture is clear to you. Now the sigma bond is formed as whatever I have said just now. You can see it is just mentioned here by head-on overlap of 2 sp hybridized orbitals, and 1 sp is coming from each carbon, carbon 1, carbon 2. And the pi bonds are formed by lateral or sidewise overlap of the unhybridized 2p orbitals or pure p orbitals, and 2 2p orbitals from each carbon will come. That means Pa, Py, Pz from one carbon and Py, Pz from another carbon. So in this way, 2 pi bonds will be formed. So this is the structure of triple bond in alkynes that we have here studied using the simplest molecule, which is the first member of alkynes, and that is AC triple bond CH, acetylene. Now we have all the 3 molecules, that is ethane, H3C CH3 or C2H6, then H2C double bond CH2, and HC triple bond CH. Now as I have said that here the 2p, though in the previous picture you can see this is blue separate, this is blue separate, but when there is lateral overlap, actual diagram is basically like this. So you can see it is continuous, right? So this is 1 pi, and then there is another pi. These two are basically hydrogens, the red balls that you are seeing here. In case of ethene, there is only 1 pi, right? And in ethane, there is no pi bond. And 2 separate cubes you can see here, which basically indicates as if it is, you can consider it as if it is tetrahedral geometry like that. Now, what about the bond energy? If you consider the average bond energy of CC single bond in kilojoule per mole unit, then CC bond, the corresponding value is 350 kilojoule per mole. For the average bond energy for CC double bond, don't think it is the energy for this particular molecule. I am saying it is average. That means compound to compound, Suppose you have total 10 compounds, and in every compound you just have one CC double bond, but that doesn't mean that in all the molecules the CC double bond will have same length. There will be a slight difference, and that may happen because of the slight structural difference, and that is absolutely expected. But when we talk about bond energy, we always consider the average bond energy. So that is why the values that I am writing here for CC double bond, it is 611. That is the average bond energy in kilojoule per mole. And for CC triple bond, now the value is even more higher. So gradually the bond energy is increasing, because to break one bond and to break double bond and then to break triple bond, obviously you just need more and more energy. So values are absolutely as expected, right? 350, then 611, then 835. Okay. Now, one extra information I'll just like to mention here, though in the chemical properties section that is more relevant, but still I'm just saying here. As you can see in ethene, because of this pi bonding, and in ethyl there is 2 times pi bonding. So these are even more reactive than ethene, because these are loosely held. Compared to sigma bond, our pi electrons are loosely held. So when you are comparing ethane and ethene, ethane is inert, ethene is comparatively more reactive, and even compared to ethene, ethane is more reactive, because now you have 2 pi bonds. The more pi bond, more loosely held electron, the more will be the reactivity. Fine. Now you can see, as I have said, cylindrical electron density. So here the pi bonding in one, for suppose y-axis or z-axis, whatever. These two ultimately will be combined together, and that is the reason you can see ultimately the structure is absolutely linear. You will not be able to differentiate the two p orbital, because all the electron densities, they are merged together. So now we can say that the electron clouds of the 2 pi bonds merge together to form cylindrical electron cloud around the internuclear axis. And this is the reason, that is the cylindrical symmetry of this electron cloud between 2 carbon atoms in ethyl. We can say that this is having a linear structure, and this bond angle, that means this AC, this bond angle is basically 180 degree. Now remember one thing, though we are saying it is 180 degree, but it may vary occasionally in some rare cases. Suppose if you consider cyclic compound, that is a rings compound where you have CC triple bond. Now in ring, this maintenance of 180 degrees is really difficult, and you will hardly see any ring structure, cyclic compound with CC triple bond, and the ring size is very small, because that is not possible. Because when the ring size is small, suppose even if I consider 6-membered ring, you cannot place triple bond here, because here 180 degree angle maintenance is not possible. So when the ring size is increased, now you can place some CC triple bond, because now the angle can approach 180 degree. But 6-membered ring, 7-membered ring, 5-membered ring, you cannot expect a CC triple bond inside the ring, because 180 degree angle cannot be achieved, right? Now, the smallest cycloalkyne, that is the smallest ring size which is found, is 9-membered ring. 9 carbon atoms are there, and it's called cyclononyl. See, this is the structure. But though this is the first cycloalkyne possible, so it is starting from 9 carbon. You cannot have any CC triple bond inside the ring for 8 carbon or 7 carbon. That is not possible. Even in this structure, this angle is not 180 degree, it is lesser than 180 degree. That means it is still under some strain. And because of this ring strain, ultimately it decomposes at room temperature. So if you want to make this compound stable, if you want to maintain its stability, you have to keep the temperature lesser than room temperature. Because even at room temperature, 25 degree, the ring can be broken because of this inside strain. Because even if it is 9-membered ring, but still 180 degree angle is not achieved. Okay. Next, we will start nomenclature. Though nomenclature, that is a general nomenclature we have seen under general organic chemistry, or you can say basic principles of organic chemistry. which is the previous unit, that is unit 12. So there we have already seen it, but still we will discuss some, especially I will discuss the examples, because rules we already know, and 2 to 3 points that are very important. We'll just discuss that. The longest carbon chain containing the CC triple bond, obviously that will be the parent chain when we are talking about nomenclature of alkyne. So right now just think that in the molecule you do not have any other functional group, as if only CC triple bond is present, and maybe some methyl substituent or halo substituent can be there, but this is the main functional group. Considering this point is important. The longest carbon chain will be that one which will contain this CC triple bond, and you have to end it with the suffix YNE, okay, to the stem name of the unbranched alkane. Stem name means, suppose if it is 3-carbon alkyne, what we call propyne. So the corresponding alkane is propane. So the stem name, if you consider for unbranched alkane, is propane, this last ANE, that will be changed by YNE. Okay. The chain is numbered in the direction that gives the lowest number to the first triple bonded carbon, written before the suffix YNE. And once the chain is numbered with respect to the triple bond, next you can consider the substituents attached to the parent chain, and they should be listed in alphabetical order. So suppose you have methyl and you have ethyl. So ethyl you will put first because it starts with E, and methyl starts with M. E comes before M. So their positions are identified by numbers. Here we will write 3 examples. So suppose we have this molecule, iodine, iodine, chlorine, then triple bond, then CH3. Now in this case, if we put numbers, obviously the numbering should be started from this side, because the first carbon of the triple bond, that should be having minimum. If you start from the other side, it will be having very large number. So that is the reason not correct. 5, 6, 7, 8, 9. So here we have substituents methyl, which is at 7 position. We have 2I iodo, that is at 6 position. We have chloro at 4 position, right? So chloro should be mentioned first because C comes before the other two. Di iodo, I before M. Then 7 methyl, and it will continue non, because total 9 carbon there. Then you can write 2-ine. Non-2-ine. 7 methyl continued non-2-ine. This is number 1. So next what we'll do, we'll put number. Now numbering will be started from this side, because if you start from this side, it will be starting from 3. But if you do it from other side, you will see it will be more than 3. So that is, it is not correct. Then 4, 5, 6, 7, 8. Here at 5 position, we have ethyl substituent. At 2 position, we have methyl substituent. So 5 ethyl should be written first. Oct, because total 8 carbon in the longest chain. 3I. Fine. Here we have 2 triple bond. Now 2 triple bond. Suppose if I start numbering from this side, it will be 1, 2, 3, 4, 5, 6, 7, 8. But instead, suppose if I am numbering the opposite side, see what happens. 3, 4, 5, 6, 7. So that 2 triple bond, 3 and 7. But if I follow the blue one, it will be 1 and 5. So obviously 1 and 5, it will win over the other. So that is the reason this purple marking is not correct. Let me erase it and we will write the name here. Here we have substituents at 4 position and we do not have any other substituent. 4 methyl, 1 5. Now you have 2 triple bonds. So it will be octa di. So in this way, when there is 2 triple bond, we will do the nomenclature. This is 2. Now the next point is, suppose you have double bond and triple bond together. Now what happens? So when we have double bond and triple bond together, and under that condition, 2 things can happen. So double bond, triple bond together, fine. But whether they are at equivalent position or not, depending on that, we have 2 separate things. Though this is already discussed in the previous unit, but still I am doing it again because this is very important. When the double bond and triple bond, they are at equivalent position. Equivalent position means whether you start from double bond side or triple bond side, both are having the same number. This is the equivalent position. Then if this is the case, then double bond should be given the lower number, right? Now, the corresponding example for this situation, number 1. So see why they are equivalent, because if you move from the left hand side, the double bond position is 2. If you move from right hand side, then also the triple bond position is 2. So that is why it is equivalent. And when we have this type of situation, numbering should be in this way. Okay. So you do not have any substituent. So it will be Heft 2 in 5 ine, because the position of triple bond is 5 position, position of double bond is 2 position. Now in will, whatever is the position of in or ine, in will always be written first because T alphabetically comes before Y. Fine. Now under this, okay, let me write it here. This is number 1. This is number 2. When their positions are equivalent, what we will do? So this is another example, triple bond. Now when triple bond is written in this way, obviously here we have hydrogen. If I have not written anything, that means it is so. So it is bromine. So see, this is again equivalent. So we will choose from this side. Total 8 carbon. And it is there any substituent? Yes, we have substituent bromo and chloro. So you will start with bromo alphabetically. 6 bromo. 1, 2, 3, 4. 5 chloro. 4 chloro. Then oct. 1 in and 7 YNE. Now when their positions are not at equivalent, then the positions are decided by the rule of first point of difference. And under this, we will see the first example, double bond, triple bond, then methyl group. Now in this case, if suppose I am doing the numbering from this side, 1, 2, 3, 4, 5, 6, 7. Now here the triple bond is getting position number 2 and double bond is getting position 4, 2 and 4. But if you do the numbering from the other side, now see what will happen. 1, 2, 3, 4, 5. So in the blue numbering, we are getting number 2 and 4. But in this case, we are getting number 3 and 5. So first point of difference, obviously 2, 4 will over the other. So this green marking is not correct and I am erasing it. Okay. And the name will be kept because we do not have any substituent. For in, always write in first. 2-ine. The second example, when their positions are not equivalent. Now I will start numbering. Suppose I'm doing the numbering like this. 4, 5. Now don't move to the other side. Both that is the unsaturation part must be in the parent chain. So if you are doing so, triple bond is getting position 2 and double bond is getting position 4. Now let me do it in another way. If I'm starting it from this side, 1, 2, 3, 4, 5. Now the positions we are getting, double bond is getting the first number 1 and this one is getting 1, 3. Now according to first point of difference, obviously 1, 3 we should give more priority. So the purple numbering is not correct. And if it is not correct, we have one substituent. So we will follow the blue one and you have 2 position, you have the methyl group. So 2 methyl parent chain total 5. So 2 methyl pent. Double bond is having position pent 1 in 3-ine. Okay. So ignoring the purple one and accepting the blue one, we are having this type of nomenclature. So I hope it is clear. After nomenclature, next is isomerism of alkynes. So alkynes show following types of isomers: position, chain, functional, ring chain. Now what all these names actually mean, that we have seen in the general section, organic chemistry section. But here our purpose is just to understand how this type of isomerism we can observe in alkynes. Now alkynes are linear, so you cannot expect any cis-trans GI, that is geometrical isomerism. That is not possible, and that is the important difference with alkenes. So here we have first, which is position isomerism. Now position isomerism means what? The functional group's position is different, and here the functional group is triple bond. So it is a different arrangement of carbon atoms in the chain, that is straight chain or branched. But first try to understand how it happens in straight chain. So suppose you have 4 carbon and 1 triple bond. Now this triple bond can be in the middle position, the triple bond can be in the terminal position. So position is different for the 2 triple bonds. So this will be the example of position isomerism. Now the first member, which is HC triple bond CH, obviously you cannot expect any position isomerism. Can you change the position of CC triple bond? No, that is not possible. You just have 2 carbon. Next member, that is the second member. This is the first member. This is second member. Now for second member also, you cannot have any other structure variation. This is not possible. So these two, that is the first 2 members, cannot have isomers. But from third member, which is butane, from third member, now you can put the triple bond either in the middle position or you can put in the terminal position. So 2 types of variation possible, right? Now, sorry, here if I draw the structure, so this I will call 1, 2, 3, 4. 1 butane, right? Another possibility is, and this will be having name 1, 2, 3, 4. This is 2 butane. So depending on the position, it will be 2. Now after that you can put branching, that is separate thing. But here position of triple bond is not same. They are getting different numbers. So that is why they are position isomers. Chain isomers. Now chain isomers, obviously chain is different. because of different arrangement of carbon atoms in the chain and straight chain or branched. Now, here also, not just first three members, chain isomerism not possible. Only from the fourth one you can have chain. Now just check the previous one. This is the third member, right? Butane is basically the third member, but here also you cannot have any chain. See, you cannot put any chain. Even if you are thinking that this CH3 put it here, but it will mean the same thing. Chain is not possible. Only from the fourth member, which is 5 carbon, it is possible. Now look at these three examples. These two you have already seen. Sorry, not the 5 carbon you have seen, but with 4 carbon you have seen how the triple bond is changing its position. So here also the same thing. Here it is at the terminal position. 1, 2, 3. So the name should be pent 1-ine. But in this case, the name is 2-ine, pent 2-ine. Now these two are related by what? These two are basically position isomerism, right? But if you consider the third one, in this case, just try to understand the relationship. It is chain isomerism both with 1 and 2. So among these three isomers, all are having C5H8. All are C5H8. 1 and 3, that is these two, or 2 and 3, these two, they are chain isomer because this methyl group, it is in chain. But if you see the relationship between 1 and 2, they are position isomer. So don't be confused between these two. They are different. Why it is important to know? Because sometimes some structure will be given and the option it will be asking that what is the relationship between them, whether it is chain, position, or some other isomerism. So that is why you should practice it. The third one is functional isomers. Now, functional isomerism is possible for alkanes because they are isomeric with alkadienes. Alkadienes means where you have 2 CC double bond. Suppose in the same molecule you have CC double bond 2 times. That is called alkadienes. And in this case also the formula is where you have 2 CC double bonds. The formula is CnH2n-2, which is just like alkynes having 1 CC triple bond, right? So this is the reason but1-ine. But1-ine is CH2 . This is but1-ine, C4H6. It is same as buta-1,3-diene, that is same formula, buta-1,3-diene. So here the numbering, if we do, this is but1-ine and the second one is buta-1,3-diene. So at one position, 3 position, there it is. And for both, it is C4H6. So these two are, that is the reason they are related to each other by functional isomer, because the functional group is different. Here we have 1 triple bond and in this case we have 2 triple bonds. So these two are having separate, different types of functionality, right? Then, sorry, this is not chain isomerism. This is by mistake, it is written ring chain isomerism. That means one structure will be ring and the open structure, another structure will be cyclic structure. It is again possible for alkynes because they are isomeric with cycloalkenes. Remember, when we have discussed isomerism in alkenes, there we have seen that open chain alkene, they are isomer to cycloalkane. Similarly, when you have open structure of alkyne, they will be isomer to cycloalkene. Fine. Both are having same formula. So here we have example propyne. Propyne is 3 carbon alkyne. So this will have formula C3H4 and it is isomeric with cyclopropene. So this is cyclopropene and again you will see this is also C3H4. So these two are related to each other as ring chain isomerism because one structure is ring, another structure is chain. Okay. Now based on this, we'll solve this problem. And it is saying that molecular formula of the fifth member of alkyne. Now this will be C6H10. Don't think that fifth member is C5. No, because the first member is C2H2. Then the second member is C3. Then 3 into 2, 6, it is 4. So whenever you are saying the member, it is one carbon extra. So that is why fifth series, it is C6H10 and it is also matching with CnH. 6 into 2, 12, 12 minus 2, 10. So it is matching with 12 minus 2. So obviously this is alkyne. So we have to write all the possible isomers and the IUPAC names. So first what we will do, we will simply consider the linear chain without any branching. So when there is no branching, just change the position of the triple bond. So you can put it at 1 position, you can put it at 2 position, this is 2, 3 carbon containing. You can put in 3, that means 3, 4 containing. So all these 3 structure, common point is all are linear, there is no branching. And keeping that factor same, you can have 3 variations. So why I am saying it in this way? Because when you will get this type of question where you have to write many, that is you have to understand all the possibilities, just do it step by step. So first restrict yourself that you will first write the simplest, that is the linear one. Once you are done with linear, all the possibilities you have covered, next go for the chain, that is any branching if it is possible. Now when there is branching, that means one methyl now we have as branching. That means in the parent, now there will be only 4 carbon. So all these are 4 carbon. The previous one, all are 5 carbon. Sorry, 6 carbon. In this case, all are 5 carbon because now 1 carbon is as substituent. So now keeping the triple bond position same. Suppose here see, it is at 1, 2 position. This is also 1, 2 position. Keeping the position of triple bond same, 1 pentyne, this is also 1 pentyne. You can change methyl, either at, you can place it at 3 position, you can place it at 4 position. So keeping the carbon chain 5 and 1 methyl substituent, here you can have maximum 2 variation. Next, what we are doing, now we are changing the position of triple bond in this 5 carbon parent chain. Now it is at 1, 2, 3, containing 2, 3 carbon. And when you have this type of placing of CC triple bond, methyl branching is possible only at 4 position. This is only possibility. 4 methyl, 2 pentyne. So these will be the 6 structures. Is there another possibility possible? See. Now it is possible only when you have, that is now the next thing what we are doing. Here it is parent carbon 5 carbon. Now it is reduced to 4 carbon. And when it is 4 carbon, you will have 2 substituents because total number of carbon is 6. So these 2 are the substituents. 1, 2, 3, 4, 5 carbon chain. So it is 1 butane, but prefix C3 dimethyl, 2 methyl substituents. Now this is 4 carbon in the parent chain. You cannot reduce it further. That is 3 double bonds. That will, even if you try to, sorry, not 3 double bonds, I'm saying that if you want to draw 3 carbon parent chain, you will see you will end up with any of these structure. You may think that why not put 3 substituents, but when you will put 3 substitutes, it will create the same type of structure. That is, it will be repetition. So these are the 7 possibilities. But suppose in the question, if it is asking that is all possible, you also have to consider whether any chiral center present or not. So see, in the first 3 structures, that is in the 6 carbon parent chain, it is not present. In the 5 carbon chain, is there any chiral center? This is not chiral center because 2 same groups are there. Now this is chiral center because you have ethyl substituent. methyl substituent, you have H substituent, and you have CC triple bond unit. So this is chiral center, so it will have one more enantiomer, and this is not chiral center. Here also you do not have any chirals. So only this methyl 3-methyl 1-pentyne you can have Arenes. So these will be the all possible isomers and the corresponding IUPAC name. Only when you will draw the its enantiomer, you will have S3-methyl 1-pentyne and R3-methyl 1-pentyne. These two will be the variation. That is because it is saying that also write the IUPAC name. So our nomenclature part, isomerism part is complete. Next is preparation of alkynes. So under total 4 to 5 headings will be there. So the first we have the starting material, calcium carbide. Now this is you can say it is inorganic compound, but this is not purely inorganic because some carbon is also there. Now what is the structure of CsC2? Structure of CsC2 is like this. Just think about acetylene, but these two terminal hydrogens are not there. Instead you have calcium. So calcium, you know, it is +2 oxidation state. So how you can think about as if it is Ca2 plus, and this is carrying negative charge. So 2 negative charge balanced by 2 positive charge. So ethane or acetylene you can prepare in the laboratory, and also it is applicable for commercial scale by the action of water on calcium carbide. So calcium carbide structure, suppose this is, then we have one water molecule on one side. And why I am writing in this way? Because in this way you will be able to understand the reaction, whatever is happening. So this part is as if making acetylene, and this HO CaOH, calcium hydroxide. So in this way it will be easier for you to memorize. Now here some impurities such as phosphine, H2S are removed. They are present in calcium carbide by passing, and how we can remove it? By passing acetylene through copper sulfate. Fine. Then calcium carbide, which is the starting material here, this how we can prepare we will see. And calcium carbide required for this reaction, we prepare it by heating quicklime. So when we heat quicklime, which is nothing but calcium oxide and coke together in electric furnace, look at the temperature, it is very, very high. Then we can make CaC2. Now for making CaC2, you are using calcium oxide. Now how you will prepare calcium oxide? That is how you will prepare quicklime. That you can make starting from CaCO3, which is known as limestone. So all these are inorganic compounds, and here these are the reactions involved. So CaO combining with carbon or coke at very high temperature, you can make CaC2. This is a byproduct, and this CaO you can make by decomposition of calcium carbonate, heating calcium carbonate. So stepwise if I see, first step calcium carbonate, number 1 you have now in your hand CaO. Next step is this CaO treating with carbon, you can make CaC2, and this is the third step where you are using this CaC2, you are treating it with water, and you are getting the final compound which is acetylene. Fine. Now by this method obviously we are getting acetylene, because from this type of structure you cannot have any alkyl group. So this is for acetylene. The first method starting for calcium carbide, remember it is for applicable for laboratory, that is small scale, and also for commercial scale. Both are possible. Now the second method is, look at the heading, dehydrohalogenation of dihalide. That means in the starting material there must be 2 halogen atoms present, and you will remove these 2 halogen, and when halogen is removed obviously it will be removed with some hydrogen. So as if it is removal of HX 2 times. 2 times you are removing HX, and that is why the name is dehydrohalogenation. Hydrohalogenation means addition of H and X, and when I am saying dehydrohalogenation, it is removal of H and X, and it is 2 times. Okay. Now under this heading B, two things are two separate headings you can see. One that depends on what type of dihalide you have taken. So two types of dihalides possible. When these two halogens are attached to same carbon, that is one type of dihalide that you will see in the next day. Today we will not be able to cover. But when they are present at 1 and 2 position, they are called vicinal dihalides. So when you have vicinal type of dihalides, that is the two halogens they are at 1 and 2 position, and you are heating it with alcoholic KOH, not aqueous KOH. Aqueous KOH, if you use, it will give you some different reaction. Remember, it is always alcoholic KOH. This is very important. Readily eliminates a molecule of HBr, not only HBr, it may be other halogen also. Ultimately, you will get vinyl halide. So when one HX is removed, you are getting vinyl halide. So see, in the first step, one H and one X, these two are removed, minus HX, you are getting vinyl halide. This type of structure is called vinyl halide. In the second step, again H and X you have to remove. But this removal is not so easy like step 1. Why? Because now you are removing this CX, which is part of double bond. So this CX bond breaking is not so easy, unlike the previous one. That is the reason now we have to use some strong base. Compared to alcoholic KOH, NaNH2, it is stronger base because in this molecule, you have NH2 minus ion, which is called amide. Sodium amide, Na plus NH2 minus. This is a very strong base, and only this type of strong base can remove HX from which is already connected to CC double bond. So vinyl halide, because of presence of bromine or halogen on a doubly bonded carbon atom, it is very unreactive, and that is the reason if you want to obtain alkyne is very good yield, a stronger base than KOH. Compared to KOH, higher strength must be required, such as sodamide or sodium amide in liquid ammonia solvent that is used. So this is general equation, and you can see here the actual equation where we have taken 1,2-dibromopropane. 1,2-dibromopropane. First you are using KOH alcoholic. You are getting CC double bond. Next you will remove this Br and H using stronger base. Now directly also you can start with the stronger base. There is no such problem. That is, you can also carry out this reaction in one step using NaNH2 in liquid ammonia. But if you are using alcoholic KOH, your reaction will be stopped here. Further reaction not possible until you are using some stronger base that is stronger than KOH. Okay. So we will end the session here. Next, we will see that starting from geminal dihalides also we can make alkanes. So we are ending the session here. Thank you for listening.